We've already seen that there are a number of identities that translate from the trigonometric identities to hyperbolic trig identities. Our quotient and reciprocal identities translate to the hyperbolic trig functions, and that's really just a matter of definition. We took those identities for the regular trig functions and we used those to define hyperbolic tangent and cotangent and secant and cosecant. Okay, we've also seen that cosh is even and sinh is odd, similar to cosine being even and sine being odd. And of course, since we can express the four remaining hyperbolic trig functions in terms of cosh and sinh, that's going to mean that they're all going to be even or odd as well. It turns out that just like with the regular trig, cosh and sich are the two that are even. The other four hyperbolic trig functions are all odd. Okay. What I want to do right now, though, is I want to look at this expression. Cosh squared x minus sinh squared x. Now, with regular trig, I know that the sum of cosine squared and sine squared is equal to 1. With hyperbolic trig, it turns out that the difference between the squares of these two functions, with cosh squared being the positive one and sinh squared being the one that we're subtracting, that gives us a nice result. And I want to just work out what that is. I'm going to have you do that in a moment. The way you're going to have to do that is by using the definitions of cosh and sinh. So cosh squared will be e to the x plus e to the negative x over 2 squared. And sinh squared will be e to the x minus e to the negative x over 2 squared. And of course, you're going to need to remember that when you square a fraction, you square the top and you square the bottom. And that when you square a binomial, the exponent doesn't distribute. You're going to have to FOIL that out. So, pause the video, work out this algebra. You will be deriving one of our fundamental hyperbolic trig identities. All right, so again, if we're squaring things, that just means we're multiplying together two copies of that thing. So I'm going to write that out. Same thing here, we're subtracting two factors of sinh multiplied together. So when I multiply this out, I'm going to get a 4 in the denominator. We'll have to FOIL out the top. So we get e to the x times e to the x. I can just add those exponents. That's e to the 2x. It's also e to the x quantity squared, but that simplifies nicely to e to the 2x. Okay. Now, plus e to the x times e to the negative x. I can add those exponents. X plus negative x is actually 0. So I'm getting e to the 0. Now I know that's 1. I'll go ahead and write that in my next step. That's kind of neat. Okay. Inside, I'm getting another factor of e to the negative x plus x. That's another factor of e to the 0. And then plus, here, I can add my exponents. I'm getting e to the negative 2x. That's equivalent to e to the negative x quantity squared. Now I'm going to be subtracting everything that I get here. I'm going to write that as just a single fraction, so it'll be clear that that negative applies to the whole thing. Again, 2 times 2 gives me 4 on the bottom. We FOIL. E to the x times e to the x is e to the x plus x, or e to the 2x. Okay. Outsides are going to give me a minus e to the x plus negative x is e to the 0. Insides are going to give me another negative copy of e to the negative x plus x. That's another negative copy of e to the 0. And last terms, a negative times a negative will become a positive. E to the negative x plus negative x is negative 2x. Okay, so what I'm going to do now is combine this all into one fraction all over 4. As I do that, I'm going to do a couple of things to simplify. First of all, I've remarked that e to the 0 is 1, so I'm going to replace e to the 0 with 1. Second, This negative applies to the entire fraction here, so I'm just going to distribute it to each term on top. So from the first fraction, we have e to the 2x plus 1 plus 1 plus e to the negative 2x. From the second fraction, I'm subtracting e to the 2x. I'm subtracting a negative 1, so I'm adding 1. I'm subtracting a negative 1, so I'm adding another 1. And then I'm subtracting e to the negative 2x. Now, a lot of the terms on the top are going to cancel. Here's an e to the 2x, and here's a negative e to the 2x. Those cancel. Here's an e to the negative 2x, and here's a negative e to the negative 2x. Those cancel. All that's left is the ones. 1 plus 1 plus 1 plus 1. Last time I checked, that was 4. So this simplifies to 4/4, which is equal to 1. So our identity is that instead of the sum of these two functions squared being 1, which is true of regular trig, the difference, cosh squared minus sinh squared, is equal to 1. Now, because that's a subtraction problem, the order matters. So, to remember what goes where, I want to remember that this is an identity, so it's true everywhere. That means, in particular, it's true if x is equal to 0. And if I remember that cosh of 0 is 1, but sinh of 0 is 0, then I can see 1 squared minus 0 squared will give me 1. But if I reversed this and I did 0 squared minus 1 squared, that would give me negative 1. Okay. So this is an identity that you should be familiar with, but if you try to approach this by just blindly memorizing a bunch of things, there's too much new information. Okay. So you want to know your basic definitions, and you want to know your basic properties of cosh and sinh. And the value at 0 is very, very important, and it helps me to remember the order of subtraction here. I can remember that, oh yeah, this is kind of like regular trig. I'm looking at the two main functions squared, but this time I'm looking at their difference instead of their sum. But to remember which one I'm subtracting from which, remembering that cosh is positive at 0, but sinh is 0 at 0, allows me to remember that it's cosh squared minus sinh squared instead of the other way round.